Hello everyone. We are giving statics lectures. Our topic, Introduction to Statics and Vectors. We will examine statics of rigid bodies in our lectures. It is also a science related to mechanics and above all to physics. So the lesson we will see is physics. Statics is the branch of science that studies the equilibrium of objects under the influence of forces. What is force? The physical effect of one object on another. It is a vector quantity. In this course, rigid bodies will be studied. What is a rigid body? It is an object that is considered not to change shape or form under the influence of forces. Even if there is a change in the shape or form of the object, it will not affect the solution of the problem. Scalars and vectors are the quantities we'll come across in this lesson. So what is the scalar quantity? A scalar quantity is a quantity determined only by its magnitude. It has no direction. For example, mass, density, volume, time and energy can be given as examples of scalar quantities. What is a vector quantity? It is a quantity that has both direction and magnitude. For example, quantities such as force, moment, velocity, acceleration, momentum are vector quantities. We represent a vector with a directed line segment. We write its name next to it. Now if we place another V symbol next to this vector, it will show its magnitude. We show the magnitude of a vector by removing the arrow above it. Sometimes we show it with an absolute value sign. We use one of these two alternatives depending on the situation. Let's look at the direction of the vector. How do we determine its direction? We determine which direction a vector is in by choosing a reference axis. The reference axis is an arbitrary line. It can be horizontal, vertical, or oblique. Any correct? We determine the direction of the vector by the angle it makes with this axis. The orientation of the vector emerges automatically after the direction of the vector is determined. In other words, after giving its direction, the angle theta, there is no need to say that the orientation of the vector is this. The orientation of the vector is line coincides with the vector. In order to understand whether the symbol we show or write is a scalar or a vector when we represent vectors with symbols, we can put an arrow on it or draw a line under it while writing by hand. This indicates that it is a vector. If we're not typing anything, just the symbol, it means it's a scalar. In the printing press or in magazines, publications, and articles, vectors are shown in bold letters and scalars are italicized letters. But in this lesson we will show it with an arrow. We'll separate the vector and the scalar with an arrow. When writing its name next to a vector, it is okay whether we put an arrow on the vector or not. It doesn't matter. We do not doubt whether it is a vector or not. It's okay if we put an arrow or not. We show that unit vectors are vectors by putting a hat on them. An arrow can be put on it or a hat can be put on it. More hats are mentioned in the literature. Unit vectors are shown with a caret to distinguish them. A free vector. A vector that has no property other than being a vector is called a free vector. For example, the velocity of all points of an object in rectilinear motion is the same. So it doesn't matter where the velocity vector is shown. The velocity vector is a free vector. Sliding vector. It is a vector with a certain line of action and the point of application can be changed by sliding on that line. The force vector in the statics is the sliding vector. It can be applied to any point on the line of action. its effect does not change. But if the line of action is shifted up or down, then its influence changes. For example, in the example in the figure, the support reactions generated by the force F applied to the rigid body change if we change the line of action. If the line of action is shifted down, the support reactions change. If it is shifted up, the support reactions change. However, the F force on the left and the F force on the right do not change the support reactions even though the application point changes. The same reactions arise. In the statics, the force vector is the sliding vector. Therefore, we can slide it on the line of action and apply it to the point we want. But we can't get it out. If we remove it, the effect changes. Fixed vector. A vector with a specific application point. The force vector in the strength of materials is the fixed vector. In the strength of materials, the deformation of objects is taken into account. Therefore, we should not change the point of application so that the effect of the force does not change. For example, if we consider an object suspended from the ceiling, if we apply the load L to its end, it will lengthen a little. However, if we change the point of application and apply the force in the middle, the change in the length of the object is different. If we apply it from the ceiling, there will be no change in the size of the object. This force does not affect the length of the object. It does not cause any change in height. Therefore, the force vector has a specific application point in the strength of materials. We cannot apply it to any other point other than that application point. We should not apply. This vector is called the fixed vector, and the force vector in the strength of materials is called the fixed vector. We will be able to do different operations when dealing with vectors. For example, we can add. When we add the two vectors, the result we get is a vector quantity. When adding two vectors, we can add with the triangle rule. When adding two vectors with the triangle rule, we add q to the end of p. We then draw a vector from the origin of the first to the end of the second. So this vector is the vector that is the sum of p and q. So, it is r. This is how we get r. Let's consider another vectors p, q. Let's say p and q be like this. Same thing again. The vector drawn from the beginning of the first to the end of the second is their sum. Another example could be this. Let be such vectors p, q. We draw a vector from the beginning of the first to the end of the second. We find their sum. Notice that if we call these p and q, that is, the summed vectors as components, the components can be greater than the resultant, the sum. Let's see whether this vector relation is valid as a scalar. This vector equation is not valid as a scalar. Because we see from the figure that the sum of p and q is not equal to r. When the length of p is added to the length of q, that is, the sum of its two sides is not equal to the third side in a triangle. Therefore, this equation is not valid as a scalar. It is a vector equation. The relation p plus q equals r is a vector equation. It is not valid as a scalar. When operating with the triangle rule, adding vectors, the resulting triangle can be any triangle. Then we can use the sine, cosine relations to find the unknowns. Whatever values we know, we try to find the unknowns in terms of them. The resulting triangle can be a special triangle. For example, it could be an equilateral triangle. If it is an equilateral triangle, then all sides are equal. P, Q, R are all equal. The resulting triangle may be isosceles. The two sides of an isosceles triangle are equal. These edges can be in P, or Q, or R. It could be any of them. Whichever sides are twin, they are equal. The resulting triangle may be a right triangle. In this case, we can find the unknowns by using the Pythagorean relation. For example, if P and Q make up the perpendicular sides, if R is the hypotenuse, then we can write R squared equals P squared plus Q squared. But there is no such thing as necessarily going to happen. The hypotenuse can be either Q or P. We change and arrange the Pythagorean relation according to the situation. The square of the hypotenuse is equal to the sum of the squares of the perpendicular sides. We write the relation accordingly. We can also do the addition with the parallelogram rule. Second, another alternative. When adding with the parallelogram rule, we bring together the starting points of the two vectors. We draw parallels from the end of each to the other. We draw parallels from the end of P to Q and from the end of Q to P. A parallelogram emerges. The sum vector of one diagonal of this parallelogram is equal to the sum of P and Q. Which diagonal? The vector drawn from the starting points of P and Q to the opposite corner is their sum. It is found this way. We see that we have divided the resulting parallelogram into two triangles with the vector R. Two triangles emerge. Considering one of these triangles, we can operate on it. Again, we can use the sine, cosine theorems, as in the triangle rule. For example, the angle beta opposite R may be known. One or more of these P, Q, R values may be known. If one is unknown, we can find it in terms of the others. For example, by writing the theorem of cosine, let's say R is unknown, P, Q, and beta are known, then we can find R from the cosine theorem. If the angle between P and Q is known, theta is given, P is given, Q is given, theta is given, for example. Then the angle theta is the angle that completes each other by 180 degrees with the angle beta. It is also visible in the figure. Their cosines are equal. But one is equal to the negative of the other. Cosine beta is equal to minus cosine theta. If we write minus cosine theta instead of cosine beta in the above equation, the minus in front of it becomes plus. We write plus instead of minus sign in the cosine theorem. This is the relation that resultant of two vectors with known angle between them and their magnitudes. Let's move on to the situation where the vectors are parallel to each other. If the vectors are parallel to each other, it can happen, then, well, this vector relation can also be used as a scalar. In cases where there are only two possibilities for the directions of the vectors can be indicated with a plus-minus sign. For example, let's take two vectors, P and Q, which are parallel to each other and in the same direction. Let the magnitude of one be 6 units and the magnitude of one be 4 units. We choose one side of the line parallel to them positive. Let's choose the right side positive. Let's substitute them in the scalar relation P plus Q equals R. If we add 6 to 4, the result is 10, positive. It makes plus 10. Plus 10 means we've got a 10 units or vector to the right. We already know from the triangle rule that the vector drawn from the beginning of the first to the end of the second is the sum vector. It is the result of the addition operation. In this way, we found R both from the relation and graphically. We found from the graph that the direction of R will be to the right. We got the same result from the equation. Consider again the same vectors P and Q. This time, let's choose the left side as the positive side. If we choose the left side as positive, since both P and Q are to the right, they get the minus sign due to their direction. P becomes minus 6, Q becomes minus 4. If we substitute minus 6 and minus 4 in the formula, the result will be minus 10. So their sum is a vector of 10 units in the negative direction. So the vector R is 10 units to the right. Again the same result is obtained. This time, let P and Q be parallel to each other but in opposite directions. Let P be 10 units. Let Q be 4 units. When we choose the right side positive, P becomes positive and Q becomes negative. We write the sign originating from its direction in front of it. We write Q equals minus 4. Let's substitute it in the formula. Let's add 10 to minus 4. The result is 6, positive, plus 6. That means we got a vector R in the positive direction. Let's draw it and show it. P is equal to 6 units to the right. This vector starts at the beginning of the first and ends at the end of the second. Addition has a commutative property. So P plus Q is equal to Q plus P. So adding Q to the end of P gives the same result as adding P to the end of Q. Let's add Q to the end of P first. Let's find P plus Q. Then let's add P to the end of Q. Let's find Q plus P. We see from the figure that we get the same result. There is also the associative property in the addition process. When adding three vectors, adding P and Q first and adding R to the end gives the same result as adding Q and R first and adding them to the end of P. Let's do the operation. Let's add P and Q first. Let's find P plus Q. We see from the figure. Let's add R to the end of P plus Q. Let's find the sum of all three of them like this. Then let's add R to the end of Q. Let's add Q and R first. Then let's add Q plus R to the end of P. Again, we see that we get the same result. Subtraction. Subtraction is a form of addition. Subtracting Q from P means adding the minus Q vector to the end of P. The minus Q vector, that is, the vector of equal magnitude and opposite direction to the Q vector. Subtraction is also a kind of addition operation. Goodbye.